So what we'll be doing, this is actually the problem. I mean, Krishna, are you there in the class?
Yes, sir.
Can you admit? Just check.
Okay. No, it's not coming to me, sir.
No, when it comes, you just see if you can admit anyone. Okay.
Okay, okay. Mhm.
So we basically focus on three aspects. One is existence of the relationships. Second one is the direction of relationships, and the third one is the magnitude. Now, what about existence of relationships? Suppose I have dependent variable y and the independent variable x. I estimate a model, and if the corresponding slope coefficient is statistically significant, then it essentially suggests that there is a relationship. The slope coefficient is statistically significant means it is statistically different from 0. And if the slope coefficient is different from 0, that means there is a relationship between x and y. So when I talk about existence of relationships, here I basically talk about the statistical significance. The statistical significance of the slope coefficient. Second one is the direction of the relationships. Given that the slope coefficient is statistically significant, whether it is positive or negative. Okay. If the slope coefficient is statistically significant, then there is a direct relationship. If the slope coefficient is statistically significant and negative, then there is an inverse relationship. So when I go for examining the validity of the law of demand for normal goods, I would expect that the slope coefficient would be statistically significant and negative. If I go for estimating a consumption function with consumption as the dependent variable and income as the independent variable, then I would expect that the slope coefficient would be statistically significant and positive. So, statistical significance of the slope coefficient or the slope coefficients, that is definitely important, but at the same time it is also very, very important to see the nature of the relationship, which is basically reflected in terms of the sign of the slope coefficients. The third one is basically magnitude. To what extent a change in the independent variable would cause change in the dependent variable. The extent. Let me give an example. If my dependent variable is demand, and if my independent variable is price of the commodity concerned, and if I convert both dependent and independent variables into logarithmic scale, then I'll basically estimate the function like log of yi is equal to alpha plus beta xi, well, sorry, log of xi plus ey. So the dependent variable is also in logarithmic scale. The independent variable is also in logarithmic scale. Now, when I estimate a model like this, can you tell me what would the slope coefficient represent? Can you tell me what would the slope coefficient represent? Anyone? The dependent variable is log of y, means log of demand. Basically, it is a representation of quantity demanded, to be very precise. And the independent variable is log of price. So log of quantity demanded versus log of price. So what would the slope coefficient represent here? What will you get if you differentiate log of y with respect to log of x? Anyone? Won't it represent price elasticity of demand? Hello?
Yes, sir, it will.
Yes.
Now, price elasticity of demand is basically a reflection of the magnitude. I'll give another example. I think somebody has. Okay. So I'll give another example, which would be very, very important to understand the role of magnitude while estimating econometric relationships. For example, government is interested to enhance growth of the agriculture sector. And let us assume that the government has limited budgetary provision to spend. Now, growth of the agriculture sector can be accelerated, say, by providing fertilizers to the farmers at subsidized prices, maybe by expanding irrigation network, maybe by providing the farmers high yielding variety seeds at subsidized prices. So there may be various options, and all can accelerate growth of the agriculture sector. But because of limited budgetary provision, the government may not be in a position to spend on all the three aspects at a time. So the government may need to prioritize where to focus first and then proceed subsequently. Now, in this case, what one can do, an econometric model can be estimated. Dependent variable is the growth of agricultural production. And say the independent variables are fertilizer use, irrigation. I'll show you some such examples with data. Then say yielding variety seeds, rainfall, temperature, etc. And after I estimate some such model, now I can compare the coefficients. The coefficient of fertilizer use, the coefficient of irrigation, the coefficient of say yielding variety seeds. But can I straightaway compare these three coefficients? Which one is higher? Higher the coefficient, I can assume that greater is the impact and the government can prioritize accordingly. But I cannot straightaway compare these three coefficients. Primarily for two reasons. One is different variables may be measured in different units. Like say fertilizer may be fertilizer use may be measured in terms of tons, and irrigation may be measured in terms of say hectares. How much area is covered under irrigation? Obviously, the coefficient of fertilizer cannot be compared with the coefficient of irrigation. So we need to standardize the variables. Second very important aspect is whether simply comparing the coefficients should be enough. Like say one coefficient is 5, another coefficient is 6. So coefficient after standardization, coefficient with respect to fertilizer is 5 and the coefficient with respect to irrigation is 6. Does it necessarily mean that irrigation has greater impact on agricultural growth vis-a-vis use of fertilizers? In this course, we will be focusing on comparing the two coefficients statistically. Arithmetic comparison doesn't matter. What matters if one coefficient is statistically significantly different from another coefficient. If one coefficient is statistically significantly higher vis-a-vis the other coefficient, that matters. So in this course, our discussion would be focusing on definitely estimation of the models, but in addition to estimation of the models, we will be also focusing on testing of hypothesis, basically to understand the relationships. And here we will be focusing on three aspects, whether the relationships exist. Second one is the nature. Third one is the magnitude. When I talk about existence of the relationships, it would be basically understood in terms of statistical significance of the coefficients, slope coefficients. Second one is the direction, which will be basically examined in terms of the sign. And the third one is the magnitude. Again, here simply arithmetic comparison will not do. We'll carry out some statistical tests as well. The second part is basically forecasting and prediction. We'll discuss a part of prediction here, but mostly we'll discuss about prediction and forecasting in econometric analysis too, particularly when we discuss about time series econometrics. But in econometric analysis 1, our primary focus would be on estimation of the model or the models, and then examining the relationships. Okay. Second, this part already we have discussed in yesterday's class. Basically, specification of economic model and then converting that into a statistical model. And here, economic theory, informal intuition, observations, all would be very, very important in specifying the economic model. And with economic model, another very important aspect, particularly in this regard, it's very, very important to know what would be the set of independent variables and what may be the most appropriate form of the dependent variable. And then we'll convert this model into a statistical model by bringing in the random disturbance term that we have already discussed in yesterday's class. Now, I'm not getting into the statistical part right now, particularly in terms of the two types of errors that we talk about while testing of hypothesis. And because all of you have done the course probability and statistics, you have clear idea about this. I'll be basically focusing on subsequently the trade-off between type 1 error and type 2 error. Say, for example, often we say that 1% significance level would give better conclusion vis-a-vis 5% significance level. Question is whether this criteria or this sort of conclusion applies everywhere. I'll be bringing in some interesting cases, like say when I'm testing for autocorrelation, when I'm testing for heteroscedasticity, whether I'd be going for 5% level of significance or 1% level of significance. Just to point out here, one very important aspect is the selection of level of significance. Why is it so? You know, in many cases we have seen the conclusions may differ depending on what level of significance you choose. Just let me give an example. A particular statistic may be significant at 10%, but it may not be statistically significant at 5%. So if it lies in between 5% and 10%, that region, then conclusion would differ depending on whether I am selecting 5% significance level or 10% significance level. So this is a very, very important aspect, and definitely we'll be discussing in detail on this, because the conclusion on testing of hypothesis would vary or may vary rather depending on the level of significance we choose. Now this is a very important aspect, that is the types of data we would be using here. In this course, mostly we will be using cross-sectional data. In some cases, we will be using time series data also, particularly when we discuss about autocorrelation problem. Now, in case of cross-sectional data, what happens? Data are generated at one point of time across the cross-sectional units. Like say per capita income in different states of India in the year 2020-21. Per capita income in different states of India in the year 2020-21. This is cross-sectional data. Time series data, per capita income in India during 1951-52 till say 2020-21. It is basically observations on a particular cross-sectional unit over time. Panel data is basically a combination of the two, where we have both the dimensions. We have cross-sectional units as well as the time dimension. But discussion on panel data would be carried out basically in econometric analysis too. In econometrics, there are different types of models. Bivariate regression model, multiple regression model. In bivariate regression model, there is one dependent variable and then there is one independent variable. In multiple regression model, there is a dependent variable and there will be more than one independent variables. In this course, we will be basically discussing about bivariate regression model and multiple regression model. To some extent, we will be focusing on dynamic models. Basically, when we are using lags, I was discussing with you all yesterday. But I will be discussing in detail about dynamic models in econometric analysis too, particularly with reference to time series analysis. Then there are nonlinear models. And simultaneous equations model. In simultaneous equations model, basically, there are multiple equations. Like consumption depends on income and some other factors. Income depends on consumption and some other factors like that. Again, simultaneous equations model would be discussed in econometric analysis too, along with logit, probit, tobit, etc. In case of say logit model, what happens? The dependent variable is binary. For example, whether you are enjoying this class of econometric analysis 1 lab, your response would be either 0 or 1. You would say either yes or no. If you are enjoying this class, then it would be 1. If you are not enjoying this class, then it would be 0. Just for example. So your dependent variable now takes only two values, 0 and 1. Then we need to apply a different method of estimation. Dependent variable is no longer continuous. It's binary. These are basically known as limited dependent variable models. There are many other examples of limited dependent variable models. Like suppose I am carrying out a survey and I'm basically trying to understand households' choice of cooking fuel. And suppose I have 5 alternatives in the list: firewood, say kerosene, say electricity, LPG, and say biomass. Now, in a sample of 100 households, I may get many households that may be using multiple cooking fuels. Sometimes they might be cooking by using LPG, sometimes maybe by using electric heaters, sometimes maybe by using firewood, like that. But again, the choice is limited to these 5 options. And how do they make the choice? What are the factors that influence their decisions of use of cooking fuels or choice of cooking fuels? So when I go for estimating some such model, then I will have different methods. Again, these aspects will be discussed in econometric analysis too. So as I said, in econometric analysis 1, we will be basically using cross-sectional data and to some extent time series data. We will be basically focusing on bivariate and multiple regression model, along with some discussions on dynamic models. Now, yesterday I talked about the random disturbance term. Now, as I discussed, the random disturbance term, the stochastic component is added into a model for various reasons. Like I might have missed out some variables. Then again, human behavior may be very random. The mathematical specification that I make, that may not be the correct one. There may be errors in measurement of the variables, like that. In theory class, we'll be discussing on this in detail, which will basically start from Monday onward. I'm just giving you a basic idea about what we are going to do in this course before I start showing you how to estimate the model in today's class, because some such basic understandings would be very, very important. Now, again, yesterday we talked about the assumptions that we make about the random disturbance term. We assume that it is normally distributed. We assume that it has zero mean, constant variance. It is independent across observations and also from the explanatory variables. Now, what happens if these assumptions are violated? Then there will be some consequences. Like if the random disturbance term doesn't follow normal distribution, then you will see, I'll be showing you in the class, the dependent variable will also not follow normal distribution. What is dependent variable yi? Yi is equal to alpha plus beta xi plus ey. So yi is basically a linear transformation of ey. So if UI is normally distributed, then YI will be normally distributed, and then the estimated coefficients will also be normally distributed. I will show you the entire mathematical derivation. So if UI is not normally distributed, then YI is not normally distributed. And then what will happen? The coefficients will not be normally distributed. And then we will not be in a position to carry out the testing of hypothesis by using the test statistics like say F, T, etc. If the random disturbance term doesn't have zero mean, then the OLS estimators will not be unbiased. If it doesn't have constant variance, then there will be problem of heteroscedasticity. If it is not independent across observations, then there will be problem of autocorrelation. If it is not independent of the explanatory variables, then there will be problem of endogeneity. Again, I'll show you the entire matrix. What are the implications of autocorrelation? The basic implication of autocorrelation is that the OLS estimators will not be efficient. Similarly, if there is problem of heteroscedasticity, again the OLS estimators will not be efficient. If there is problem of endogeneity, then the OLS estimators will not be consistent. So autocorrelation will result in inefficiency, heteroscedasticity will result in inefficiency, and endogeneity will result in inconsistency. So that's what I was telling you yesterday. That simply estimation of the model or the models and carrying out testing of hypothesis would not be enough. We also need to see if the assumptions are valid. If the assumptions are not valid, then we need to redefine the model, we need to re-estimate the model until unless the assumptions become valid. Because violation of the assumptions will have some consequences on the OLS estimators. Now, these are some formula. I'm not discussing about this. I'll be just uploading. You please have a look. What I'll be doing, I'll be showing you a very simple example. It's an example of a bivariate model where I have taken profit after tax by sales as the dependent variable. Yesterday we were discussing this, that there may be two alternative measures of profitability. The dependent variable is profitability and the independent variable is advertising intensity. You all have studied in microeconomics that when there is product differentiation, advertising plays a very, very important role, and accordingly, firms' financial performance may be affected or influenced. So here we are taking profitability as the dependent variable. Now profitability can be measured in different ways. Like here I have measured it as PAT by sales, and if you just go to the next slide, it is PBT by sales, profit before tax by sales. Now important question here is, if there is any difference in the regression results, Now, if I just go back to the previous slide, what do I see? The estimated model is statistically significant. What is basically reflected in F? This is the F statistic, and this is the level of significance. It is less than 0.01. So the estimated model is statistically significant at 1%. Now, what happens to R square? It is 0.19. Means around 19% variations in the dependent variable, that is profitability, is explained by advertising intensity. Now, if I just move on to the next model, sorry. That was profit before tax, and this is profit after tax. Here also you see the estimated model is statistically significant, but the R square value is much higher. When I use profit before tax by sales, I get R square value 0.19. And when I use profit after tax to measure profitability, I get R square value 0.70. Of course, both the models are statistically significant. In both the cases, we see that advertising has significant impact on profitability. But when I'm using profit after tax by sales as the dependent variable, the R square value is 0.70. And when I'm using profit before tax, the R square value is 0.19. Subsequently, I'll be showing you some examples where, depending on how you measure the variables, it may so happen that the coefficient doesn't turn out to be statistically significant at all. This is what I was pointing out in yesterday's class, that measurement of the variables should be very, very important. But again, in many cases, we may have certain constraints like, say, data limitations. We may not be in a position to measure a variable the way it should be. Then we use basically the closest proxy. Like if I measure profitability, hello.
Sir, I had a question that can you explain these terminologies like G stats, F R squared, adjusted R squared, advertising
Yeah,
intent?
I'll do that. I'll do everything. I'm just showing you some examples where basically I am highlighting the issues that we'll be focusing on in this course. Are you getting my point? Now, have you done probability and statistics?
Yes, sir.
In probability and statistics, that course, I think this T stat, F stat, these things were discussed.
No,
If
sir.
not, you can tell me. I can. I mean, we can. I think these are part of that course, no?
Yes, sir, but in online some statistics part was not covered for almost all the batches.
Okay. We'll then focus on that. We'll focus on that.
Sir, and also it will be helpful if like you could just give a quick recap because it's been like almost a year.
Sorry.
So like it would be helpful if you could give just like a quick brush up or something because it's been all.
Absolutely. So what we can do in the class on Monday, okay, we can focus on basically the basics. Like here, frequently I'll be using 4 statistics, test statistics. One is Z, second one is T, third one is chi-square, fourth one is F. Okay. Now every test statistic has its own definition, and perhaps you can recall that all the 4 test statistics are somewhere or other related to the assumption of normality. Z statistics, say for example, it follows standard normal distribution. So it is linked with normality assumption. Chi-square, it is basically summation of square of Z. Again, it is linked with normality assumption. F stat, say for example, it's a ratio of 2 chi-square distribution. I'll discuss these basics so that it becomes clear. R square is basically an indication of explanatory power of the model. To what extent the estimated model can explain variations in the dependent variable. So here, say for example, this estimated model explains 19% of variations in the dependent variable, that is profitability. Adjusted R square is basically R square adjusted for degrees of freedom. Like I can show you the formula. This R bar square is basically the adjusted R square. This R bar square is basically the adjusted R square. And here it is being adjusted for degrees of freedom. You can see. I'll focus on these aspects, like say what is meant by degrees of freedom for TSS, total sum of square, degrees of freedom for residual sum of square, degrees of freedom for explained sum of square. All these would be very important concepts. So I'll start as somebody was pointing out. Yes, please.
So what is K is degree of freedom and what is N in this formula?
No. K is not degrees of freedom. K is the number of coefficients. Number of coefficients being estimated, and N is the number of observations.
Got it.
I have some Word documents also, what I had developed last year. I'll share all these things. And then on Monday, as somebody suggested, let us start with the basics. Definitely that would be very important. And if the basics are clear, then we can proceed faster subsequently. So in this example, basically what I tried to show you all, that measurement of the variable may influence the regression results. Very simple example. In this case, profitability is being measured as profit after tax by sales. In this case, profitability is being measured as profit before tax by sales. And you see, here the R square value is 0.70. And we say higher the value of R square, better is the model. Or higher is the value of adjusted R square, better is the model. So here advertising intensity is explaining 70% variations in profitability. And here in the other example, advertising intensity is explaining only 19% variations in dependent variable or profitability. Now definitely suppose 2 students are estimating some such model, and one is using profitability measured as profit after tax by sales, another student is measuring profitability as profit before tax by sales. in both the cases, as far as this example goes, the estimated model is statistically significant. In both the cases, advertisement has significant impact on profitability, but the explanatory power, the R-square value differs. R-square value is also known as goodness of fit. We normally say higher the R-square value, better is the model. But again, I am adding a caution. While higher R-square value signifies or signals a better model, a model with low R-square value may not be necessarily discarded. Again, a very high R-square value may signal the problem of multiplied. So these are some concepts. I understand that many of you might be wondering, I mean, what I'm talking about. I'm just trying to highlight certain issues, certain concepts that we need to focus on in this course. Like here, the issue is basically measurement of the variables, how that may influence the regression results. Okay, so with this, I'll stop for a while, and what I'll do now, I'll